First of all, if you go to the website, you should be able to see the slides. Okay, please do that if you, because we're starting to have more codes. Perfect. It's good. Anyone who's answered a different thing for the fourth question, you're all good. We love all of your responses all the same. No response is gonna be treated differently, especially this one. So if you want to follow the slides, please do, because I'm taking a lot of time to, instead of just distributing PDFs, which I hate, you're just going to be able to look at the courses, the slides. The assignment one will be on the website, is on Canvas, it's live. We just haven't updated the table. We will do that. I just saw that today, that the table isn't updated. Yeah, we will do that. Okay, so today I'm going to talk about in general data and data cleaning, and then given how much time we have, Mehdi will show you more practical stuff. Okay, so in general, what we start with asking the question, what even is data, right? There's a lot of things that are around the world that are collected, artifacts like traces from activity, things that we collect. Anything can be data, right? But here we're going to think about how learn vocabulary of understanding how we describe data. Okay, so the first thing I want you all to know is structured data. Structured data is an organized type of data. It fits neatly into rows and columns mostly, right? Things are nice and clean like a table. Unstructured, these are things that are actually more often in the world, right? Chats, texts, images. These have no organization. Everything is different in every data set, right? These are called unstructured data sets. We're gonna, in this course, we're gonna learn how to deal with both in terms of data science. Especially, we're gonna do some basic, the beginning will be more with structured data and machine learning with structured data, and then we'll learn how to deal with specifically text as an unstructured data source. And then we're going to learn how to use LLMs and other sorts to do stuff. If the time allows for the course, at the end, we're going to be able to build a little bit of small agents with LLMs that do some NLP tasks. Again, most real world data is unstructured. And a lot of times we create a structure from unstructured data. A very clean example is, hey, if we have a bunch of tweets, let's count the words in them and then create a table of the word counts. That's the type of thing that you can do. Okay? But let's start with the most basic type of structured data, a table. Table generally has columns, right? These columns are the variables in a data set. Okay? Variables. And then we have rows. The rows are observations. Each row is an observation, is an item in our data set. And then obviously the cells are the values. So let's say that this data is about character appearances in different episodes of different anime. So the show is Jujutsu Kaisen. So that's one observation for episode 1. And Gojo has appeared 12 times. This is how you read a table. I think everyone knows how. And again, this is the second observation, this is the third observation, and so on and so forth. Okay? So columns are variables, rows are observations, and cells are the values of the data. A concept that's really important, especially since you're doing data science, is the concept of tidy data. Okay? Let's look at it. A lot of times you will see a data set like this with these columns, right? Each column here, even though it is a variable, right? So for episode 1, it says Gojo. First of all, you don't know what this number is referring to. It just says Gojo, okay? However, let's assume that we know that this is the count, the same count of appearances. If you want to access information about like all the characters. Let's say you wanted to add all the characters that showed. This will become really wide, right? It will have one column for each row, right? Accessing columns by names is difficult, right? Every time you have to say, okay, give me the Gojo column of episode 1. This is called a wide data set. You'll see it. It's easier to read. It's more compact, right? It's harder to analyze because adding a new character is a new column, and columns are harder to deal with in most times. Okay? So now let's look at a long format version of this data set where we repeat observation. Now, each observation is not an episode here, is a character. Okay? So we have for each character, again, which used to be a column, we'll have one row. And then now we can say, okay, for episode 1, give me the character that equals Gojo and then how many appearances. See, it's like you can ask questions. You can say, okay, for episode 1, give me the row whose character is Yuji and then how many times they have appeared. Okay? So this is getting a data to a tidy format allows you to do things for it. For example, you say, what is the average appearance of all the data? You can just get this column and then just get the mean of it instead of taking all the different columns. We're gonna show you an example in other data sets. Okay? So you can then also group by one character. You can say, for example, there's an operation called group by that you can say, okay, group each episode and then give me the count or averages. So one thing that you're going to later learn how to do, and the code is here so you can try it, is getting a wide format data set. And let me actually try to go to, and then let me show you the wide format data set. As you can see, you have all these different columns, right? And there is you can run some code to make it into a long format. So for example, melt is an operation. And here, see, now we turned it into all the different episodes, all the different characters, and then we can do easy things for it. Like you can find the ones that have appearances more than 15. Okay? You can ask questions so much more easily. So your data set will look like this, essentially. Okay, moving on. Another data format that's more prevalent when you deal with web data, essentially, is called JSON, JavaScript object notation. This is how objects are, almost how objects are described in JavaScript. And because JavaScript is the programming language of the web, it's how it's structured. You can get it with APIs. So these are basically in Python are similar to dictionaries. These are key value pairs. So you can ask, okay, give me the show, and then it will give you the Jujutsu Kaisen, and then you can get the episode, and then you can have an array. So this is why it's nested. You can have now multiple observations within the appearances. It can be more unstructured. So it's good for nested or hierarchical data. But you generally want to turn it into something more structured. Another format that is prevalent is XML. OpenStreetMap, I think, uses XML for some aspects. Everything is nested. So you can get an episode, and inside an episode, you can get different characters. You will have attributes for each character, and you can get those. Anyone who's seen or taken any course knows that this is basically also HTML is this. HTML is a subset of XML. It's very much similar, but has a specific character to it. So they're basically the same, yeah. Another data format that is pretty interesting these days, if you're on YouTube, you might see a lot of discussions around it, is Markdown. Markdown is a sort of format where you can basically write these things, and then the browser or one software can render it into correct HTML. Okay, so if I inspect, as you can see, this is the exact same markdown, but in my browser it's turned into H3, right? Or the asterisk has turned into bold, so strong. Okay, so this is a data format, and these days it's been it's increasingly used as a format for AI agents. So if anyone uses OpenClaw or I don't know Cloud Code or anything, that the things that you set for the agent is claude.md. It's a markdown file. Why? I don't know, but it's closer to written language. It's not bloated. It's less tokens than HTML, but it's rendered into HTML. Okay? So yeah, you can actually use this format for a lot of different cases. Okay, so unstructured data, we're not going to focus much on, but let's just see examples of it. Okay, for example, text. This is an email team. The final cut for episode 1123 is ready for review. Luffy's Gear 5 sequence runs for whatever. Okay, and then, so this is just, any email is different. That's why it's unstructured, but it also has metadata. Each email could have some sort of structured data describing it. So you can know from whom to whom this email is, or the date, or the subject, or the length could be the metadata, how many characters. So you can use these to filter these texts and ask questions from them. Images are unstructured because images are basically pixels, and each pixel is 3 numbers, RGB, and then these are turned into these matrices that are used in, hey, again, a lot of AI now uses these sorts of data. Audio is the same. Audio is a temporal type of data. The length could vary. From that sense, it is like text, but it's a sequence of amplitude samples over time, typically this much per second, and then you processing it is different and it's hard, right? So generally, a lot of us don't really deal with audio that much. Even in a lot of AI systems where you talk to it, it turns it into text first and then feeds the text because it's easier for AI to handle it. Newer models have audio capacities, capabilities, audio understanding capabilities, but audio is a very sort of rich type of data, right? Because the voice, the tone, the amplitude contains not just words, but meaning, but emotions, sarcasm. You can read a lot more information from it. Okay, so far we've learned the basics of what data formats are, but let's look at the tools that we have in our disposal. Okay, Python, obviously the one that we're going to use for this course. R is another really good example. When I was in grad school, I was in a Python camp and I sort of, oh, R is stupid. Nowadays, in a lot of my tasks, I actually use R because it just makes my job so much easier. But also Excel and Google Sheets are another tool for you to use. So Python is, for data science, has a lot of different libraries. We've started to use them like pandas, numpy, matplotlib, scipy, or scikit-learn, right? And it looks like this. You can load data into a data frame through the pandas library. Again, we've done this, and then it'll organize it for you in a very complex data format, but then you can do things with it. Like, for example, you can get the top 5 rows in a data set. You can do operations with it. You can wrangle the data with this. So the syntax looks like this, for example. Again, you're going to see it. You can group by, and then you can aggregate it, and then you can sort the values. And then this is what the results will be. In any case, you can basically go back and run these codes for yourself and play with them. You can visualize the data. Anyone who's taken my visualization class knows that we use something like Vega Lite or D3 to produce. These are libraries that have different philosophies. You can make a bar chart by giving X and Y coordinates, and then you can style it. So it's a different philosophy than how we think about encoding and channels and stuff. There's a library called Altair that is basically Vega Lite. There's another library called Seaborn that is more opinionated. See, when you make the bar plot and give it the X and Y axes and the data, it also draws some error bars for you for some reason, right? So then you can see why you can remove them by passing some arguments. Or, again, we're not going to use it, but I really suggest that you try it on your own because it's amazing. Has a whole lot of libraries for handling. It can do anything that Python can, but a lot of the data are like libraries are like designed for you to deal with really good data, right? You can also run Python from it, right? So it's a bit different than Python. So variable assignment is like this, right? But it's really interesting. You can pipe things together. So you can say check-ins and then pipe it to another function and then pipe the outputs to another function. Again, if you're interested, go look at it. It's really fun. ggplot is the library that you can use. Honestly, it's so much better than anything that Python has. And then it has a lot of community around it. You can make amazing visualizations with it. And it uses a grammar of graphics type of work where we are more familiar with. Lastly, Excel. You want to open your data sometimes, look at it, maybe correct something, maybe move something around. You can sort, filter, do pivot tables from wide to long, group data. So you can do all sorts of stuff. No code's needed. Or you can also run code within it. And now they're advertising all these LLMs that run within it that you can ask it to do stuff. And you can share it easily. So a lot of data can be shared as Google Sheets. But it's generally considered small data. So whenever you have more than 1 million rows, it's hard to open these files, but then you can use Python or something to look at it. Lastly, notebook environments is basically the output of a data science project. Why it's so important to do it like a notebook? Because it has code, it has data, it has computational results, and it has written analysis all at the same time, right? It provides Markdown. Again, another thing that you can do is when you annotate in a notebook, you're using Markdown. All of this is together, and it's also reproducible. You can run it again, get the same results because you load the data, you do everything in one format. It's tweakable. You can change a parameter, rerun it, see what changes. It's documented because you can do text and visuals at the same time. You don't want to load raw data, do some processing in code, edit the file, some file by hand, and go change the data and do more processing. You want to have a process that's very much documented from A to Z because a data scientist wants their work to be reproducible. Okay? You've seen Jupyter, how that works. We have it here. This is a version of Jupyter. These are cells. These are, again, not going to focus it. We've already seen it. You see the code output, and then your interpretation goes the same way. Okay, collecting data is another interesting thing. Data comes from a lot of different ways. Sometimes you can get data from open sort of government sources where they publish the data like data.gov, census, city open data portals. Canada has a bunch of different things. Kaggle is another example, has a lot of data sets, competition notebooks. There are academic repositories, Google Dataset Search, UCI, ML Repository, Harvard Dataverse. These publish open data sets. And then there are open domain-specific data sets like IMDb, my anime list, OpenStreetMap, etc. Okay? These have data. Wikipedia is a data set, so you can use it. Other data sets are proprietary. Google, Meta, Netflix have enormous data sets, but they don't share it with you because that's their basically bread and butter. That's how they make money. Sometimes, though, you can get APIs, access to their data sets through something called application programming interfaces. But these are controlled and rate limited because you're hitting their servers to give you data. Basically, is a structured way to request data from a service programmatically. So for example, in Python, you can get data from OpenStreetMap. There's the endpoint here that you can hit a request to, search, send these parameters, say your query is Vancouver, the format you want is JSON, you can get the results and get the response, and you will get something like this. It'll get you the latitude and longitude and the type of the query. OpenStreetMap's API is open. You can host it for yourself. But if you want to use their service, they have a rate limit. Twitter, remember those two books? The book that I wrote, Social Media in the Contemporary City, a lot of it is on Twitter data. We could basically stream the data. The data would come in just constantly, a sample of 1% of all tweets in real time. We could filter it, could search historically, right? And then if you paid a little money and university would do it, you could access all of the history of data. Okay, use sentiment analysis, event detection. We'll learn some of these methods in this class. But after Elon Musk came, things changed. Now you can get 100 tweets, can do some basic with $200 a month with 15,000. Again, it's just crazy. Had it been this time, a lot of my research would not be possible. And then when there's no API, you go get the data yourself. There's spidering and then there's scraping. Basically, you want to extract the content that you want. Now, spidering is just get the whole HTML from the website. You can bring it and it's unstructured, it's the whole thing. But you can also extract structured data from a website, for example, because pages are just HTML and you can translate it into something you want. These days, you can basically ask an LLM to do this for you. It's trivial. You can paste raw HTML into LLM and ask it to give it a prompt, right? To a clean JSON array with fields XYZ, it'll do it for you almost with no error, right? But this is not practical at scale. Token costs add up fast. You don't want it to read every website. So the real way is how the people in the streets do it. Yeah. Is using a library like Beautiful Soup, for example, where you get the output as HTML, raw HTML, and use it to parse. For example, you can select all the titles and then from the titles get the text and strip it. So now I just want to show you in general, it's something a lot of you would be interested in. So let's say you want to get, sure, I agree, middle of teaching, I don't know what I agreed to. You want to get this table. You can give it to LLM and it will do it for you, or an agent, but every time it will process a lot of tokens. But if you come here and click on inspect, you'll see that there's a structure. This is already a table. So you can, with something like Beautiful Soup, you can learn the structure and you can find, okay, for each div, find me all the div that have the class detail. And then through that, you can get the one that has, you can find it, right? You can get the title. Let's find it. Okay, so you can say, okay, give me the one that has the class this. Hover info trigger. I think all of these will be hover info trigger. The class would be the same, right? So then you can easily find them. And then you can run a for loop and collect the data, turn it into a table. It's something that I used to do a lot for a lot of my courses. So again, it's a good practice to think about how you might want to do this. And again, this is something that would require a lot of knowledge, but honestly, you can also, I really suggest that you learn, but you can ask an LM to give you the code to do this. these are some of the basic data collecting stuff. You can ask it to get all of these and then give you the code to click on the next page and they get the next page and so on and so forth and collect your own data. Be careful when you collect data like this because the website might block you. So you need to be nice and look it up. There's different ways to be nice when you scrape data. And this is how all the big companies are basically doing things these days. Lastly, you might end up building an application, a website. You can collect logs. You can get information on how people are using your system. For example, let's say you have buttons. You want to see at what time people click on the buttons that you have, right? So one thing that you can do is to add a new event listener into your click event for a button and then record all of this and then send it to a database. Okay, you will get a data set like this in your database, or you can download it or print it, and then you'll have data. So a lot of times when you build something, you want to look at it later, how people use it, you can log it yourself. It's a really good practice to do that sometimes. And you can log the physical world. It's really fun. If any of you is interested enough, you can just get a Raspberry Pi. They've gotten more expensive, but they're still very cheap. You can build sensors for yourself and put it somewhere. You can do all sorts of sensors, and it will collect the data for you. And it will save it. You can ask it to send somewhere. So you can build your own data set. For any of your projects, if you end up wanting to do any of this, let's talk. It'll be fun. Okay, last part. Data cleaning is the main section of today. Garbage in, garbage out is the main notation, main motto of machine learning. You need to first clean your data. Oh, dang. I messed up. Today is really not the day. But
That's all right. Things happen.
outlier data cleaning. Okay. So yeah, cleaning is really not optional. You really want to do it for many cases because you will get wrong answers if you don't do it. And we'll see example of them. And try to don't lose your original data. Don't mutate the original data. This is coming from experience. Once I just destroyed my database by writing over it and I just lost my data. I did something wrong. So we learned about errors in the book. Error is a data that is permanently lost or unrecoverable due to some mistake. A sensor goes offline, there's some problem, a server crashes, there's problems in the real world that cause data to be problematic. Artifacts are a systematic distortion introduced by processing. Scoring system changes how it counts, a platform policy changes trigger mass behavior. This is an artifact, right? So you can think about cases where some of these things happen and treat your data cleaning differently. Artifacts can be fixed, errors cannot. Okay? So you look at your data before you model it. You ask, does this look like what I expect? Surprises are either insights or artifacts. Figure out which, right? Sometimes you say, oh, I'm surprised that this happens. Maybe that's something interesting. Sometimes this is a problem in your data. And most surprises turned out to be artifacts, in my opinion. So let's look at an example. Anyone played Helldivers 2? It was a game that came out a while ago. It's a really fun game. It's a multiplayer game where you go into a map and fight aliens. And it's very funny and it's very patriotic. It makes fun of patriotism and stuff. It's a really good game. These were the scores. I don't know if you remember, but the game had a really good, overwhelmingly positive scores on Steam. Then suddenly, Sony announced that the accounts should be merged or something. So people started review bombing. And then policy was reversed. And then people's ratings came back. So if you want to calculate the average rating, would you take consider this part? Probably not, because oh, this something happened that's not a true representation of what the game is. It's something external. It's the policy. So the game didn't get worse, the data did. And in a lot of cases, people are already mad before the movie is out because there's some sort of woke problem or something, and they just give it 0-hour reviews, like zeros before even the game is out. Is that a representative, a good review? No. So some game, would you count this? Sometimes you wouldn't. Another thing that we want to look at in data cleaning is outliers. You first plot the distribution using a histogram, look at it and see whether it looks right. Then you have methods. I've shown you IQR already, but let's look at it again. Another one is z-score or z-score to find values from the mean, values that are far away from the mean. Then you ask why these exist. You don't just delete the outliers. So let's look at this fake data on the games that I played. This is a true story, but the numbers are wrong. Anyone can make a guess why Slay the Spire 2 for me is close to 1,000 hours, Balatro the same, but other games were around this time. Any guesses? The number of hours that I played these games. Yes, a real gamer is Econ because, yes, 1,200 hours. I just let it, it was just open and I left. I left to go to bed. I played it a long time. Exactly. I was AFK. But the hour is being counted. It's an outlier. So if I plot it, do the histogram, the number of games that are close to this are here. And these two games, because I played them a lot, they would probably be around here, 200 or something, but they're now around here. They distort the data. Okay? So you can calculate the IQR. The IQR is very simple. Again, this code is available to you. You get the first quantile and the third quantile, and then you calculate the distance or the difference between them, the size between the third and the first. And then the lower bound for your IQR is Q1 minus 1.5 times that range. And the upper bound is that, right? So let's say for my data, Q1 was 18, Q3 was 15. So these are numbers where 25% of the data is less than that, and then 75% of the data is less than this number, okay? And the range between them is 33. So the lower bound is minus 31, which is non-existent. This is not a real bound, but anything higher than 100, based on this data, can be considered an outlier. And if you run this, you will get these two games like this. So this is the upper bound, and then these are the games that are outside of it. So this is a method. It's flagged, it's robust to the skew distribution. You've already seen this. This is a box plot. We're going to use this tomorrow as well. Boxplot has this information in it. The points that are outside of these whiskers are the outliers that are outside the IQR. Another metric is the Z score. It's really unfair. I used to say Z in Iran. Then I came to the US and they rewired my brain to say Z. And I'm not in Canada and people say Z again. So I have to say Z. Anyways, the Z score is how many standard deviations is a value away from the mean. Okay? You already know we talked about standard deviations, and this gives you that, right? So, for example, you can say anything outside of 2 standard deviations away from the mean is an outlier, and that would be Slay the Spire 2 in this case. So you can calculate that. We know how standard deviation is calculated from the previous lecture. That's a common threshold. So was this an outlier or an artifact? Balatro and Slate Aspire both have 847 and 1200, right? So the IQR and Z score both flagged it, but the reason is simple. The game was left running. So removing them blindly would be wrong without checking why. Maybe you can get it, reduce it, get the number of times you were asleep out of it, or look at the different averages, right? However, you don't want to remove it because you now have an answer. Always investigate before you delete. Okay. Sometimes there's problems. You have missing values in your data sets. In pandas, they would look like NANs. And those missing data, you can, first of all, you can remove them. Anything that has missing data, you can say delete. It's possible, but you're losing data. If missing values are rare, you can do it. If it's random, you can do it. But if it's an actual systematic problem, maybe missing value is a feature in your data set, then you want to take care of it. Sometimes you can fill it with the mean of everything else or a category, another category. So maybe for Balatro and Slate Aspire, you just put the mean of every other game. Maybe. Or maybe if there was another game, another card game that I used to play last year that I didn't go AFK, you can use that as a ballpark of how much I would play. Anyways, there are ideas. You have to think about it. You can forward fill it. For timelines, this works. So assumes that the last known value still holds. So let's say if you have a times temporal thing, if it's missing, you can just go and say, oh, fill it up. If it was missing, just add yourself to the next one. Lastly, there are problems in strings or data matching. You've seen a lot of it. Let's say we're looking at these 4 games, this Elden Ring in our data set. However, all of these different ways Elden Ring is written is different for a programming language. So you can't count it. So you have to clean it somehow. Maybe you basically need to normalize these. So you can get the title, you can lowercase them, you can remove any other artifact, you can remove spaces, and then put them into the clean. And you'll get a correct column. Another way is time zones. Sometimes your data has time and they're collected from different time zones. You want to convert them to a unified time zone because different time zone things mean differently. Units in general, if something is in kilograms and then another thing is in pounds, all of these you have to look at it, right? Heights, if some people are put their heights in 1 centimeters, let's say you built a health app, right? And you want to do calculations. If someone, I always put centimeters, some people do pounds. You have to unify them. You have to have a function to clean that data for yourself. And with that, I just want to say, now it's gotten so much easier because a lot of these things you can automate. You can really quickly ask AI to give you code. It's all good, especially for this part. However, it still is a big chunk of a data scientist job because you have to think about why the data is missing. And that's the challenge that we put for you for that 15. Really, we just want to look at the data and find them. It's like a discovery phase. So try to do that yourself. Look at the data. Use these techniques that we taught you and today and tomorrow and do it. Yes. That's a very good question. That's a very good question. So sometimes, first of all, some problems in data, you can't always fully clean the data. But if you have, let's say, instances, you can, if we have other values, let's say you have the last name or the father's name, maybe that's different. You can use that, right? You can, if you know whether the reason they're different, you can add a 1 and 2 to differentiate them. As long as they're unified and normalized, it's good for your data. So you have to look at a strategy to fix that problem. Very good question. Thanks for reading that book. Yeah. Okay. That's all from my end.